All right, so we've made it. This is going to be the last video in my controls series. And this video, what we're going to do is we're going to talk a little bit about keyboard/cascade control. Um, this is kind of similar to the idea of next loops, if you're familiar with kind of coding vernacular. And so what we're going to do is we're going to, of course, simulate kind of a cascade controller. Um, we're going to use our frequency response analysis um, to kind of approximately give us some degrees of stability, and then we're going to simulate that closed loop response. So without further ado, let's talk about it here. What is cascade control? So we're given a system in prompt number 1 here, which describes a cascade controller scenario. Let's go ahead and start talking about, here we go. Let's start talking about a block diagram for this cascade controller. So we're told there's an inner loop, and we're told there is an outer loop or a master loop. And all this means is that we're going to kind of have multiple controllers working in tandem to kind of accomplish the same goal or affect the same output parameter here. So I think this is kind of easierly shown in the block diagram format. So I'm going to start with that, and then we're going to kind of talk about it. So in this format, we are, again, going to have a set point coming in. That's going to be our R of S. And then it's going to be met with some output here. And there's just going to be some subtraction, and that's going to give us an error. That error is going to go into our outer controller here. So this is GC. And this is going to be a PI controller. And we know that because our outer controller is going to be PI. Okay, so then we're going to go into our inner loop here. And what's going to happen is basically now we're going to have kind of another set point take place here. So here's going to be our other set point. And we're going to go into another controller here. In this case, we're going to call it a valve. And that valve has the function n over s plus 1. That's the gain of our valve here. Perhaps I should label these opposite. This is going to be some form of PI control. That's what we're looking for here. Specifically, the controller gain parameter in this case, and GC. Okay, so the output of that controller is then going to go into some sort of cascade controller with inner loop process transfer function, inner loop proportional gain. Oh, I did this wrong. So our valve is going to be our process here. Hold that. Okay, this is going to be our process. And we're also going to have a good old-fashioned proportional controller with a gain of 1.2. So this is just going to be a KC or GC in. And of course, this will be GC outer. Then this is kind of our G E inner. And then we need GP outer. And the way that that's going to happen is we're going to send an error signal down here from this function, return that back to our GC, and then multiply it again by 1.2, and then have it go through the process. Okay, and then we need an outer process function here. And so this outer process function is going to be represented by this formula here. So 0.12 e to the negative 5s over 12s plus 1. So this is our GP outer. And then that output is going to be our true output here. And then we're going to, of course, send back the signal. There we go. So I straightened those lines out so that hopefully we can see it a little bit better. But this is kind of our process control diagram. Again, look that in each of these loops, we don't have a measurement device right now. We could go ahead and throw a measurement device in there, and of course that would just be another transfer function. Another thing to note about our process transfer function is that there is a time delay. Signified by the exponential of the negative 5s term there, we can realize that that represents some sort of time delay. Remember, if that were in just a true time domain, we would see some sort of t over theta term, and that would represent our time delay. Okay, so our goal here is going to be to find the controller gain to a yield approximately 30 degrees of phase marginal stability. What does that mean? That means that, remember, again, negative 180 degrees is the maximum stability that we could go to. So we really want to be at about negative 150 degrees of stability. And that's kind of what we're going to attempt to find here by manipulating our KC parameter. So this is going to be solving this problem. We're going to do this a little bit rudimentarily by simulation. I'm going to go ahead and program all of this out, and we're going to get the wrong answer first, okay? And then we're just going to mess around with our tuning parameter, our proportional controller, until we yield negative 150 degrees of phase stability. So we're going to plot all this up into our two Bode plots, and then we're going to go ahead and grab our simulation so we can see what's actually happening to the process. And I think this is a really good example to kind of signify the relevance of simulation, because obviously, if we were attempting to truly tune this controller, we wouldn't want to do that in a sense where we would actually be manipulating the process output, right? That would be really bad. But through the simulation, our process output can go as unstable as we want, and we're not messing with, a 500-gallon reactor vessel capacity or something like that. The other piece is that with simulation, we're gaining the ability to manipulate time in a way that we couldn't do that if it were truly in the process. Now, obviously, anytime we do this kind of control parameterization and calculation like this, what we're going to end up doing is actually running some sort of test in the field to actually ensure that the calculations we did are significantly true. However, this gives us a really good starting point to say, hey, your system's not going to go crazily unstable theoretically. And this provides a more robust basis for that than simply throwing a wild guess out into the wind of, hey, this is the guess for our controller parameter. So again, we're constrained by this reset time here in this case, which makes our problem really easy because we only have one parameter to manipulate. And so that's why we're going to go ahead and just generate the Bode plots here. So let me start actually by pulling up our code from last time here. We're going to go back to this Bode diagram. The reason being it has all my inputs in it already. Okay. And so what we're going to do is we're going to attempt to code in this this guy here. So I'm just going to go all the way down here and start coding. Let's actually run all this again. All so that our imports go ahead and download successfully. Solid. Okay. And while we do that, let me start thinking about how we're going to do this here. Okay. Run, run, run. Here comes all the inputs. Okay. This is our bot from the last video. Awesome. Perfect. Okay. So let's go ahead and start to code this out here. Let's see. So let's start with kind of our outer loop. Our GB is our outer loop of our process, right? We said that's going to be 1 over 0.1 times S plus 1. Similarly, we have a controller gain for our inner process here, and that's just simply a proportional controller at 1.2. So then the G, let's say, closed loop inner is going to be what? GC inner times GB divided by 1 plus GC inner times GB. Right. That's our inner loop. Should it? Hold up. Yes, that's our inner loop. Cool. So let's go outside and get our process loop with our actual PI controller. This will be our outer loop. GC outer is going to be what? It's going to be 1 times 1 plus 1 divided by 0.5 times S. Okay. And so again, right now we're signifying 1 as our controller gain. We don't really know that yet. This is just a straight guess. But we're going to go ahead and check this out here. So, well, maybe let's put 1.5 in initially and see what happens. So then our GP outer, well, we can just call it GP because we call it GP, is going to be just our process function here. So remember, this is the one with time lag in it. -5 times S divided by 12 times S plus 1. And then, of course, GCL outer is simply going to be what? Everything on the top. So GC outer times GC inner times GE divided by 1 plus GE outer inner times GP. Okay. See here. Okay. The reason is NumPy can't deal with the symbol S there. That's why we threw that error. Okay, so next, what are we going to need to do here? We're going to need to generate our Bode plots. So let's go up here and just kind of copy down this code. And make corrections to it here. So we can go from like -3 to 5 to 0 and put 500 stubs in there. That looks good. R and I look pretty good. This looks pretty good. This is going to be exactly the same. All those calculations are the same. So then let's just go ahead and grab our plotting here. Okay. Anything different about this that we want to do? Actually, I think that all looks good. Let's see what this does. Okay. So, again, we want to have about 30 degrees of marginal stability. So that means when this hits 150 here, we want to have this okay, hold up. Let me say this effectively once I can find 150. Perfect. Okay, so that's about 0.1. When that hits negative 150, we want our amplitude ratio to be 1 here. And so we can see that at 0.1 as our frequency, we're still at 2. So this isn't. Let's go ahead and shrink this down, 1.2. Again, this should be the same, right? We're not changing any of these calculations. 0.1 still, 0.1 still at about 2. Negative 150. Right about 2. Okay. And so that gives us the marginal stability that we're really looking for here. Well, I don't like this. I think I'm missing something. Yeah, G needs to be GC outer times GC inner times G. Okay, so now when we hit negative 150 here, about 0.07, I'm not really close to 1. Negative 150, 0.073. No, we're not there yet. See if we can troubleshoot this real quick here. All right, so it appears that we've simulated the system correctly. Basically, we've already implemented this one here, which has given us the 30 degrees of phase margin stability that we requested. So let's go ahead and plot out how this looks physically if we were to simulate it. So we're just going to use the sim function from earlier here. Let's see what I call this G here. I call it BCL outer. Then use a lambda t here. 1 n equals 500. Equals 1. Well, we can make 1, I guess. And then make another figure. X equals y y, mode equals lines. And then big dot update layout. Equals 600 height equals 400 and template equals body. Okay, so what we're going to do here then is mess around with our controller gain until we get to a value that looks about right, and that looks about right. So we're very, very close here. 5 too much. 4, 5. Okay, that looks pretty good. So 1, 2, 3, 4, 5. We can see how quickly we can assume steady state again. And again, right here when we get to 1, there we are, 0.088, 0.08 corresponds with about 30 degrees, give or take, of phase angle stability. So thus, we've successfully constructed our control schema for Cascade control. Hope you've enjoyed this series. I've been Michael. I hope to construct some videos in the near future about kind of IMC control. However, we'll see with my applications to medical school upcoming. How quickly this videos actually end up coming out. Thank you very much. See you later. Bye.